Dear colleagues and participants, it is my great pleasure to introduce today's speaker of the Al-Khwarizmi Applied Mathematics webinar, Shuhei Shibata. Shuhei is a master's student at Keishu University, enrolled in the Joint Graduate School of Mathematics for Innovation. His work lies in probability theory and stochastic processes, with a special focus on self-similar Gaussian processes and a remarkable model called the elephant random walk. For those who may not be familiar with it, the elephant random walk is a non-Markovian stochastic process where each step depends on the entire history of the walk. Because the walk remembers all its previous moves, the model exhibits rich behaviors that differ drastically from classical random walks. This memory effect has become an active research topic in model probability and in physics. Shuhei has distinguished himself through both the depth and the clarity of his research. He received the Excellent Poster Award at FMFI 2024 for his work on the infinite collision of two elephant random walks. He has also presented his result at the NUS probability seminar during a research visit to Singapore, highlighting the international recognition of his contribution. More recently, Shuhei has co-authored new results on elephant random walks through the lens of classical limit theorems for self-similar Gaussian processes, and he continues to develop innovative approaches to understanding these memory-driven stochastic systems. We are truly fortunate to have him with us today, and I am confident that his talk will be both engaging and insightful. Please join me in welcoming Shuhei Shibata, and please, you can start.
Okay, so thank you for introducing me. So my name is Shuhei Shibata, and I'm a graduate student at the Kyushu University in Japan. So I'm glad to be invited this nice conference, and also I was also very happy and very surprising to be received by email from Professor Rafik. Okay. So today I will talk about the elephant and monk, especially functional limit theorem for elephant and monks on general periodic structures. Okay. Okay, so outline is here. So first, I introduce the concept of elephant and monk, and the in this presentation, so we have two topics. So first topic is the elephant and monk on general periodic structures. Okay, so this is the main topic in this presentation. And if you have time, if we have time, so we will talk about the collision problems for two independent elephant and monks. Okay. Oh. Okay, so first I introduce the elephant and monk on Z. So elephant and monk is a non-Markovian stochastic process which has a complete memory of its entire history. Okay, so the first step x1 of the elephant is +1 with probability q. Q is gives a deterministic, and -1 with probability 1 minus q. And for it, the natural number n, given the past steps from x1 to xn, then we define the n plus 1 steps by this formula. So xn plus 1 is equal to, in the case of plus xun with probability p, 1 minus xun with probability 1 minus p. So we explain this part easily for this easy figure. So when given the past step from 1 to 4 steps, then we want to determine the fifth steps. Okay. So then, for example, we choose, for example, the third steps uniformly, and then it moves in the same direction. So in this time, so right direction with probability p, or opposite direction. So in this case, left direction with probability 1 minus p. Okay. So for example, if we choose the second steps uniformly, then it moves in the same direction. So in this time, the left direction with probability p, or right direction with probability 1 minus p. So UN, it means we choose uniformly, and plus is means same direction. So, yes. So with probability p and with probability 1 minus p. So, and p is called the memory parameter, and UN is uniformly distributed on from 1 to n, and independent of xi. Okay. Then, so the sequence xi generates the one-dimensional quantum Monk Sn defined by this. So S0 is defined by 0, and Sn is the summation of xi. Okay. This is the quantum Monk on Z. And so next we introduce the asymptotic behavior of elephant on Z. So it is well known that the asymptotic behavior of elephant and monk depend on the memory parameter P. Okay, especially on Z, the critical memory parameter P is equal to 3/4. Okay, and so if P is less than 3/4, then law of large number, this law of large number satisfied. And P is a critical case, then the scaling is square root n log n, and this law of large number is satisfied. And if P is greater than 3/4, then Sn divided n power to P minus 1 converges almost surely the random variable L. So random variable L has a continuous distribution, which is not Gaussian. Okay. So if P if,
sorry, I think log n is inside the square root, no?
sorry, so let's square L root log n. Yeah.
Okay.
Sorry, thank you. Yeah. Sorry, so square root L log n. Yeah. And so if P is nearly equal to 1, so this case, so it moves, elephant and monk continues to moves in the same direction of the initial steps. So it diverges fastly, so by scaling n to b minus 1. Okay. Okay, so and so elephant and monk has a fluctuation if p is less than or equal to 3/4. So CLT and LRL satisfy if p is less than or 3/4. Okay, so this LRL satisfied, this CLT satisfies, and this LRL satisfied. So yeah, scaling is square root and log n. Okay, thank you. Okay. Okay, that's also the concept of elephant and monk. Okay, so let's start the first topic, the elephant and monk on general periodic structures. Okay, so in this time, so we consider the elephant and monk in high-dimensional settings. So there are many papers about the high-dimensional setting for elephant and monks. So, for example, Berg and Rowling in 2019, so they investigated the simple behavior for multidimensional elephant and monk on ZD by multi approach. And later, they showed the simple behavior of the center of mass of the elephant and monk. And Gary, Rowley, and Lecter, they investigate the distribution of in super diffusive regime. And also, so Akin shows that recurrence and transience of multi-dimensional elephant and more. Okay, and Currier and Rowling in the same year. So they provide an alternative proof of the recurrence in the diffusion regime for plane. And in this year, so Berg studies asymptotic behavior of the multi-dimensional phantom with stops. Okay. And also, so Bertin studied functional limit theorem for the elephant on ZD bipolar approach. Okay, so that most previous works concern the case of Z3. So in this time, so we consider more general structures. Okay, so especially we extend this Bertin's works from Z3 to more general structure, such that this triangular lattice or hexagonal lattice, or this is called brick wall. So we want to extend more general case. Okay. 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 So let's set the stage. Okay. So first, given to finite set of distinct vectors u and w in Rd, and for fixed integer m and m prime, and m and m prime is the greater than 2. Okay, and we call the element of u and w step vector, since we will define a random walk whose steps are drawn from this set. Okay. Okay, and so we distinct the cases, case u is equal to w and the u is not equal to w. So first we discuss the u is equal to w. Okay. And then so in this case, we consider the same groups generated by them. That is so this case. So gamma is the set of the summation kiui, and ki is the natural number over 0. Okay. So we obviously we can obtain the fact that this gamma satisfies the semigroup, but here we assume that this semigroup's gamma is a lattice in Rd. So that is, it is a discrete additive subgroup that span Rd as a vector space over R. Okay. And for this case, so gamma is analyzed as a single colored vertex set owing to the structural indistinguishability of all vertices. Okay, so we provide some typical example of gamma in U is equal to W case. So for example, if U and W is the set of plus minus E1, plus minus E2, and plus minus ED. So EI is a standard basis vector of RD. Okay, then so gamma coincide with the Z3. Okay. Another example, U and W is the set of plus minus the vector 1, 0, and the vector 1 half, square root 3 over 2, and plus minus minus half, and square root 3 over 2. Then gamma coincide with the triangular lattice. We can obtain this figure. Yeah. So there are typical example of gamma. Okay. Okay, so and next, so we discuss the case u is not equal to w. Okay. So in this case, we first define the semigroup gamma 0. So gamma 0 is the set of the summation of kiui plus summation of ljwj, and we add the restriction. This is the summation of ki is equal to the summation of lj. So k and lj are the natural number or 0. Okay. So then we assume that this same group is a lattice in RD. And then we consider this gamma. So gamma represents the decomposition of gamma 0 and, and the translated shift as shifted set gamma 0 plus u. Okay, so we explain this part for typical example, hexagonal lattice. Okay, so if U is the set of U1, U2, U3. So U1 is the vector 0, 1, and U2 is this, and U3 is this. And W is the set of minus U1, minus U2, and minus U3. So then, so gamma 0, we consider the gamma 0. So, and if we started from at this we studied at this vertex, this red vertex. Okay. Then, for example, K1 is equal to 1 and L2 is equal to 1 and the other parameters is equal to 0. So then this part is U1 plus W2. Okay. So then U1 plus W2. So U1 is this. So it moves U1 and U2 is W2 is minus U2. So minus U2 is minus U2 is this. This moves. Okay. So we arrive at the red point. Okay. So this is a red point and other example. So K, for example, K1 is equal to 2 and L2 and L3 is equal to 1 and the other parameters are equal to 0. So then this part is 2U1 plus L2 plus L3. Okay, so 2U1 plus L2 plus L3. Okay, so then this start 2U1, so 1, 2, and L3 and L2 and sorry, W2 and W3. So minus U2 and minus U3. So minus U2 and minus U3. So we are also arrived at the red point. So it means that so gamma is a set of the red point vertex set. Okay. Okay, so gamma is the red vertex set and gamma 0 plus u, so shifted set. So gamma 0 is the red point and by shifted u, so for example, the vector u1 of u and shifted. So U1 is shifted this. So this part, this each vertex is shifted. So we can obtain the vertex set of blue point. Okay, so gamma 0 plus u is the set of blue vertex. Okay. Okay, so that's all. So and we define the vertex classes by ZU is gamma 0 and ZW is gamma 0 plus u. Okay. So we introduce gamma given by this composition to represent a setting in which each vertex is assigned a specific color as in the hexagonal lattice. Okay. And moreover, under these settings, we enforce the alternating rule. So for any z in ZU and any I from 1 to m, then z plus ui in ZW. Also for any z in ZW and z plus wj in ZU. Okay. So this rule ensures that the worker always remain within gamma. Okay. So that's also gamma is therefore a bipartite graph with vertices classified according to the decomposition in this decomposition and is analyzed as a two-colored vertex set as in the hexagonal lattice. Okay. So okay, we also present a typical example of gamma. So hexagonal lattice is satisfies, and also brick wall. So brick wall is U is the set of plus minus E1 and minus E2, and W is equal to plus minus E1 and E2. So this figure is a brick wall. So this assumption is satisfied. Okay, and also another example, so plus minus U1, plus minus U2. U1, U2 is the vector 1, 2, and 1, minus 2. And W is this. So then the gamma is coincide with Z2. And also this example, plus minus E1, plus minus E2, the vector 1, 2. And W plus minus E1 and plus minus E2. And this is also, gamma is also the Z2. Okay. 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 So that's all. So we can set the framework gamma. So now, next we introduce the definition of the elephant of gamma. Okay. So given dimension D and U and W are the set of step vectors, and sigma 1i and tau j are the random sequence taking values in U and W respectively. Okay. And first, we discuss the case U is not equal to W. Okay. So in this elephant walk, so we consider elephant walk that alternatively move between two vertex classes, so red vertex and blue vertex, by making a step chosen from U when at the red vertex, and a step chosen from the W when at the blue vertex. Okay. Okay, so at time n is equal to 0, the elephant is started from the origin at the red point, and at n is equal to 1, the elephant takes a determinate step. Sigma 1 is equal to ui0. So the elephant choose the direction, a deterministic direction, I0. Okay. I0 is I0 is from 1 to m. Okay. And wait, second, and at the n is equal to the 0 elephant takes a determinate step. Tau 1 is equal to W0. So at time n is equal to, the elephant choose the deterministic steps, the deterministic direction J0. Or J0 is in from 1 to m prime.
Sorry, I0 and J0 are chosen randomly or are fixed? I0 and J0 are fixed or chosen at random?
Fixed, yeah.
Okay.
Yeah, no, deterministic. I, yeah, and we can do, yes, yeah, at random. Yeah, fixed. Yeah, no random. So we can do the fixed the direction I0.
At the beginning, we fix I0.
Yeah, fixed, yeah, I0.
Okay, for n equal 1 and 2. Okay.
Yeah.
Okay.
Also J0, okay, yeah. Yeah. So subsequently, so the elephant proceeds by alternatively visiting the two vertex class, red vertex and blue vertex, and generates an alternating sequence of step choice. So step sigma 1, tau 1, sigma 2, tau 2, sigma 3, tau 3, yeah, and so on. Okay. Okay. So
And how,
then,
sorry, how we choose sigma 2, sigma 3, tau 3, sigma 2, tau 3? How we choose?
Yeah,
How we choose
yeah.
them?
We introduce
Okay.
later.
Okay.
Yeah,
Thank you. Sorry.
yeah, yeah. Thank you. Okay. So for each n, so given the path step from sigma 1 to sigma n, and from tau 1 to 1 and tau n, then we define the n plus 1 step by the two process by this. So, and this means that, so when we want to determine the sigma n plus 1 steps, then so we choose only from the sigma 1, from sigma 1 to sigma n only. So in other words, so we choose the odd step. We choose only the odd step. Okay. On the other hand, tau is tau n plus, when we want to determine the tau n plus 1, then so we choose from the even time steps. Okay, even time steps. Then and it moves in the same direction with probability p, and in the opposite, also the other direction with each with probability 1 minus p over m minus 1. So and and the random variable un and wn are uniformly distributed from 1 to n, and we assume that the un and wn and sigma, the process sigma I and wj, are mutually independent. Okay. That is a sigma 2, sigma 3. Yeah. Okay. And then, so the secant sigma I and wj generates the elephant on gamma with S0 is defined by 0, and S0 is 0 defined by this. So, for example, S1 is equal to sigma 1, and S2 is equal to sigma 1 plus tau 1, and S3 is equal to sigma 1 plus tau 1 plus sigma 2, yeah, and so on. Okay, so, and, okay, so we call this process type 2 elephant and mock. Okay, so also we also note that, so again, so type 2 elephant and mock alternately moves between the red point and blue point by making a step chosen from U and from W. Okay, okay, so this is U is not W equal to case, and we introduce the elephant moves on gamma, so red point, blue point, red point, blue point. And in brick wall, so red point, blue point, red, blue point, so moving, yeah. And also, so this example, so introduce previously, so U plus minus U1, W1. So this example shown this figure. So red point and from U, which is from U, so moves blue point and red point, blue point, red point, blue point, and so on. So it's like moving, okay? So this example is also. Okay, so this is a quantum mock on gamma. So, and also, so next we discuss the case U is equal to W. So, but so we know that since the process in this case depend on the entire path trajectory, so not depend on the only even time or odd time. So entire path trajectory. So we describe the definition separately from the U is not equal to W case. Okay. So then the elephant mock on gamma with S is equal to 0 is defined by the summation of sigma I. So we call this process type 1 elephant mock. Okay. And so when U and W is equal to this case, and that is gamma is ZD, Then we recover the multidimensional elephant and mock introduced by Berg and Rowling in 2019. Okay. Okay, so up to this point, we have established the setting for gamma and defined the elephant and mock on gamma. Okay. Yeah, so and for analyzing the next, so for analyzing the elephant and the mock, then we use the Fourier process. Okay, so the Fourier process and the elephant and mock are very closely related. So in other words, to obtain the asymptotic behavior for elephant and mock, so we only study the asymptotic behavior of the corresponding process provided by Johnson in 2004. So, but I will not discuss the process in this time. So, because it takes it takes a time to explain it. But this is a very important analysis. Okay. Okay. So, and by employing the Fourier analysis, we have the critical memory parameters. So, and we have the critical memory parameter PCM. So PCM is equal to m plus 1 over 2m, and PCM prime is equal to m prime plus 1 over 2m prime. So this is related to the process of sigma I, and this is related to process tau j. Yeah. And when u and w is equal to this case, and this is m is equal to 2D, then PCM is 2D, 2D, so 2D plus 1 over 4D. So this is corresponding to the Berg and Rowling and Beltane case. And especially for D is equal to 1, PCM is 3/4, so corresponding to the original phase transition. Okay. Okay, so for some, and later, so we will explain the my result. So for some result, we need to distinguish cases depending on the critical parameters PCM and PCM prime. But here we present only the main cases. Okay. Okay, so let's go to the main theorem. Okay, so firstly, we obtain the strong law of large numbers. So let Sn be type 1 or type 2 elephant and mock. Then for all P, we have the almost shear convergence, this almost shear convergence. So Sn scaled by n converges almost surely to half U bar plus W bar, where U bar is the summation of Ui divided to M, and W bar is the summation of Wj divided M prime. Okay, so for this typical example, triangle lattice, in the triangle lattice case, so U bar and W bar is equal to 0. Also, hexagonal lattice is also. Then, so this right hand side is equal to 0. And brick wall in U bar is equal to this and W bar is equal to this, but entirely, so U bar plus W bar is equal to 0, so this part is 0. And for example, so U bar is the plus minus E1 plus minus E2 and the vectors 1, 2, and W is this set. Then, so W bar is equal to 0, but U bar is this, not equal to 0. So this example as shown figure, this figure. Okay, so then, so limiting is this. Okay. Okay, so next, so we discuss the functional centralism theorem in diffusive case. So let Sn be type 1 or type 2 elephant and mock, and memory parameter satisfy this condition. Then we have the distribution convergence in the Skorohod space, and time is 20 minus the expectation term and scaled by square root n, and convergence in distribution, the process Wt, and Wt is a continuous Gaussian centered continuous RD-value Gaussian process with W0 is equal to 0. And for if S is smaller than T, then the covariance structure is specified by this form. Okay. And so A is equal to MP minus 1 over M minus 1, and CA is 1 over 1 minus 2A. And sigma U is summation of UI minus U bar and UI minus U bar transpose divided M. And sigma W is also WJ divided M prime. Okay. So especially in this covariance matrix, terms, so we provide covariance matrix for typical example. Okay. And firstly, so Z3 case. So if U and W is the set of plus minus E1 and plus minus E2 and plus minus ED, then especially so sigma U and sigma W is identity. So this term is identity. And also triangular lattice and hexagonal lattice. So sigma U and sigma W are identity. Identity matrix, And this also is identity matrix. Okay. And moreover, so in the brick wall, so and especially the matrix term, so sigma U and sigma W is this. So and this is not identity matrix, but this is a diagonal matrix. Yeah, but this is not identity matrix. Okay, and this example introduced previously. Then sigma U is the set of this. Sigma U is this matrix, and this is not identity matrix, but it's a diagonal matrix. Okay, sigma W also identity matrix. Okay, and in this case, as shown this figure. Okay, then sigma U is this matrix. So so this is not identity. So this is not diagonal. So it appears correlation terms. Okay. And also sigma W is identity. Okay, so this is a covariance matrix. And DMARC for diffusive case. So where U and W is this. So this coincides with the result of Bertin. And furthermore, in this Bertin case, it is well known that the coordinates of the limiting process Wt can be expressed as independent noise reinforced Brownian motion. So introduced by Bertin. Okay. So in general, so in our case, so Wt can be represented by the following Wiener integral. So this integral, we can obtain this integral representation. Okay. So where Bt and Bt prime are independent standard dimensional Brownian motion, and if we only consider this term, and sigma U is the identity, so this term coincide with the integral representation of independent noise reinforced Brownian motion. Okay. And moreover, so as shown by Lamperti, so that limiting process Wt appearing as such a function limit theorem is known to be a self-similar process. So Wt is a self-similar process. Okay. Okay, so this is a diffusive case. So the next critical case. So let Sn be type 1 or type 2 elephant on mock, and the parameter satisfy this condition. Then, so time 2 and power t minus this term scaled by this property proper scaling converges to Wt. So Wt is a center congruence Gaussian process, and the covariance structure is specified by this. Okay. Okay, so when you and W is this, so this coincides with the result of Beltane, and also so Wt can be represented by this, where Bt denotes the standard dimensional Brownian motion. So if sigma u and so sigma u w is equal to sigma u plus sigma w. Okay. So then, when sigma u and sigma w is the identity matrix, then Wt is standard d-dimensional Brownian motion. Okay, and finally, so we discuss a super diffusive case. So let this condition, and then the following almost trivial functional convergence holds. So for type 2 elephant and the mock Sn, so we have the Sn is minus the expression term divided by n power a. So in this case, so a is greater than 1/2. Okay, so then convergence in distribution T A L, where L is some RD valued random variable different from 0. Okay. Also for type 1 elephant and mock, we have this convergence. We have this convergence result, and where L tilde is some RD valued random variable different from 0. Okay, so in this time, so we are interested in the distribution of L and L tilde. So we calculate the expectation on the covariance. Okay. So assuming U bar is equal to 0 and W bar is equal to 0, and that the first step are chosen uniformly from the M directions. Then the expectation of L is coincide with this, and by this condition, and this sum is equal to 0, and also the expectation L tilde is this and is equal to 0. And in the covariance term, and we obtain this term, and sorry, so sigma u plus sigma w. Okay, so we can obtain this formula, and by this condition, we can obtain this formula. L tilde is also this. Okay, so we know that unlike in type 1 elephant and mock, the distribution of L for type 2 elephant and mock depends on the behavior up to time n equal to. And for L tilde, when U and W is this case, so we recover the result of Berg and Rowley 2019. Okay, so that's all. So and up to this point, so we discuss the first topic. Okay, so next, and we discuss we turn the story. So second topic, so collision problem of two elephant and mox. Okay. Okay, so and now we want to consider the whether two elephant and the mox can meet infinitely often on Z. Okay. Okay. So then we can obtain this result. Okay. So, and Tomoyuki Shirai is my supervisor and me in this year. So let Sn and Sn prime be two independent elephant and mock on Z. In this case, on Z, with the memory parameter P and P prime respectively. Then we can obtain this figure. Okay. And so this figure shows that if P and P prime is less than or equal to 3/4, so as shown this yellow area, then they can meet infinitely often, almost surely. But and if P or P prime is greater than 3/4, then they cannot meet infinitely often. Okay. And so the case P equal P prime, P prime red line, is studied by Roy and Takei and Tanemura in 2024. So instead we extend their result. Okay. And also we obtain the asymptotic behavior of the distance. And Roy, Takei, and Tanemura, if P equal P prime is less than 3/4, then this LRL this LRL can be obtained. And if P is less than or equal to 3/4 and P prime is less than 3/4, and in general P and P prime in general P is not equal to P prime, then we can obtain this LYL. And if P equal P prime, then this term coincides with this right hand side. Okay. Okay, so and we prove this LIL by the LIL for self-similar Gaussian process. So this is interesting topics, but in this time we shall not go into this. Okay, okay, so summary. So first topics, we investigated function Lewis theorem for elephant on general periodic structure, including Z3, such as in triangular lattice and brick wall, and so on. And so next, second topic, we investigated whether two independent elephants on Z, each with a different memory parameter, can meet infinitely often and also obtain the asymptotic result for the distance between them. Okay, that's all. Thank you so much.
Thank you for you, Shuhei, for this nice talk.
Yeah.
Are there some questions, please? Some question? Please, if you can go to slide 16.
16, yeah.
Yes. If we choose, we don't choose the same P. I mean that probability that sigma equal to sigma u n equal P, and probability that tau n plus 1 equal to tau w n equal to P prime. Are there some difficult to study this model? We not choose the same probability.
You mean that this part is P and this part is P prime. So in general, P is not equal to P.
Okay,
right?
okay. Okay, so it is not necessarily the same probability. Okay.
Yeah. We pose this. This part is the same, but
In general,
yeah. So yeah, and so result is so and this was the P and the P prime is
are equal,
right.
no?
Yeah. Yeah, maybe we
Okay,
could, but
okay,
yeah,
okay. No, no problem. No
yeah,
problem. In the slide 19, slide
19, yeah.
19. Okay.
Yeah.
Why the appellation of type 1 and type 2 elephant random walk? Why type 2 elephant random walk? It is your appellation, or are there some phenomena that specific to for the appellation type 2? Why 2? Why not 3, 4? Why 2? Is
Oh,
with respect
oh
to the
yeah.
dimension or something else?
Oh yeah. So, okay. So this is in our case, so this is a bipartite class,
Okay.
right? But we could consider the more general, but say, more general setting. So, okay, sorry, right. Okay, so for example, we could consider this concept of Kagome lattice. So this is uh, this sorry, this figure is divided by the three distinct color vertex set.
Okay.
So red and blue and green. So, but unlike the select vertex case, so the number of visits to each vertex class is not deterministically balanced. So, in our case, so the, the number of visits to each vertex is deterministic balance. So this fact is very important for
Okay.
analysis. Yes, but so a different type of analysis is required. But in other case, so we can establish the same class of our result when the work is enforced to move the critical cyclically between
Mhm.
the vertex. So red, blue, green, red, blue, green, red, blue, green, red, blue, green. So this is the same class of our result. But elephant is, in general, elephant doesn't move this cyclically. So this is a different type of analysis
Okay.
is
Okay.
okay.
Okay. Thank you. You mentioned that there are a connection with a kind of polyerns. What is this connection? And what kind of polyerns we consider here? What type
Polymer.
of urns
Mm.
is connected with your model here, for example?
Yeah. So uh, elephant and Fourier model connection. Yeah.
Yes.
Mm. So okay. So this slide. So xn is xni is the number of balls of color at time n, and consider the process xn. Then so we can obtain this duration. So
Uh,
the
and,
elephant.
and what represents y here for the urn? So x and I is the number of colors of type I in the urn at time n. And y and j, what represents?
So xni is the number of ball in the arm,
Okay.
and ui is uh, introduced introduced previously. So the vector and UI and direction of UI. So this means that so the extent to which the elephant moves in this direction, UI and WJ, is governed by the number of balls X and I and Y and J.
Okay. Mhm.
Yeah, right.
Okay. Okay.
So yeah, okay.
Okay. Please, slide 21.
21, yeah. Okay. 21. Okay.
Is it surprising that the limit of Sn divided by n, the limit almost surely, is free of p, of the memory parameter p?
Oh, um,
The,
for all.
yes, u bar and w bar are free of, I think, that are free of p. No, they are free of p.
Sorry, one more. Okay. Two, three. Sorry, one more time. Okay. One- Sorry. And uh, W bar is, hmm? Sorry, I can't understand
Okay.
your question. So,
Okay. I
how,
mean that the limit almost surely of Sn divided by n, I think that it is free of P. It does not depend on P.
uh,
On the
yeah,
part.
scale by n
Mhm.
does not depend. Yeah, does not depend
Okay.
on parameter. Yeah,
It is
yeah.
surprising. No, it is for all P
Uh,
we have the same limit.
yeah, it's
Okay.
not surprising. Yeah,
Okay. Okay. Slide 27, please.
yeah, 27.
Uh, why L and L tilde are not Gaussian? Are they Gaussian or not? I think
But,
that there are not Gaussian,
yeah, not Gaussian. So,
as in
yeah,
Berkey 2018. But why they are not Gaussian in your model?
yeah, and by the Polian approach. So, Johnson. So,
Okay.
L is
Mhm.
not Gaussian. Yeah.
Okay. So you have no other information about the distribution of L and L tilde. No other information.
So, no other. No.
Information about the distribution. We have only
Yeah, yeah. We can only the expectation and the covariance. So,
okay.
but we want to the consider the other distribution, property of distribution. Yeah.
Uh, I have a general question on extension. Do you expect that similar functional limit theorems would hold for continuous time analogs of elephant random walks or for non-uniform memory kernels? Your approach can be extended for continuous time analogs of elephant random walks
Oh
or
yes.
uh, or for non-uniform memory kernels.
This part. Huh?
In general, general question.
Yeah. So, sorry, I cannot answer your question. So one more, please. Okay. Okay. I can understand your question.
Okay, I
Uh,
mean that.
uh,
Do you think that we can have similar functional limit theorems, convergence of the process to the Gaussian process,
uh,
uh, be true also for continuous time elephant random walk when the elephant moves continues in time? Continues
uh,
in time.
elephant, continue time,
Yes,
continue.
continues. Yes.
Yeah, maybe yeah. No, I don't know.
Mm.
Yeah,
Okay. Okay.
yeah.
Just for the first slide or the second slide, I think number two. I think uh, number one. Number one.
Number one.
Yes, please. Or number two. Number two. When you present the almost sure limit of the elephant random walk.
Oh,
You are
this,
true. Okay. Number one. Okay, please.
this.
Number one. Two. The
Yeah.
second slide. Second slide.
Second slide. Oh,
Yes. Okay.
oh, that is that.
Okay. Here it is true. It is my remark. It is not true. I have a mistake. Sn
Yeah.
point 2i Sn divided by square root of n, only square root of n, all multiplied by log n. It is true
Yeah,
like
yeah.
this. Okay. But
Yeah,
for the central limit theorem, we have the
yeah.
speed is the square root of n log n. Okay.
Yeah.
Thank you very much. Are there other questions, please? If not, we have to thank again Shuhei Shibata for this nice talk, and see you after 2 weeks with a new talk. Thank you.
Thank you so much.
Thank you for you.